Hello. So, in this video, we're going to be doing the root test. So, root test as follows. Suppose an is a sequence of real numbers and an is eventually non-negative, right? So again, we've done that in a previous video. That means that, there's some capital N, so that if little n is past capital N, then all the ANs are indeed non-negative. And this is important if we're going to be talking about, progressive roots. So the root test then says, so if the nth root of an is bounded by some alpha where that alpha is less than 1, then this thing is going to converge. And I put here a very common saying, so by way of sort of introducing you to common parlance and notation in the field. So this is saying for n, the nth root of an for all sufficiently large n. And so this is the sort of counterpart to the eventually piece, right? So when in mathematics we say something sufficiently large, we mean that, again, there's some capital N such that if we're past that capital N, it should work. And sort of importantly here, I'm saying for all sufficiently large n, meaning that every little n past that capital N, this should be true, right? Just like eventually it is always non-negative, okay? So essentially, putting aside the eventually non-negative and for all sufficiently large, the idea here is that if we take the nth root of an, then at some point it is bounded by alpha strictly less than 1, means it converges. If on the other hand it's greater than or equal to 1, then we know that the series diverges, right? And if we can't say either one of those, right, then the test fails, which is totally possible. If you have, all the even ones are 1/2 and all the odd ones are 4 or whatever, then a bunch of them will be bigger than 1, but a bunch of them will be maybe less than 1. I guess that wasn't quite good because that'll still go to 1. Well, no, yeah, that works. It'll be less than 1, albeit close to 1, for all of the ones that were 1/2 and greater than or equal to 1 for all the ones that are sort of too big. So this doesn't mean that you get all possibilities, is what I'm pointing out here. There's also the corollary. So this is the Cauchy's version of the root test, right? Cauchy was all about the limits. So he says, suppose the limit as n goes to infinity of the nth root of an is alpha. Then if alpha is strictly less than 1, you have the series converges. And if the alpha is strictly greater than 1, you have the series diverges. This is the one you probably learned in Calc 2, depending on when and where you took it. So as a footnote, so I'm going to prove the root test. I'm not going to prove the corollary. That should be up to you guys. I will point out that it should take a form very similar, or an approach very similar to what we did with the ratio test when we did the limit version of that. So rewatch that video or go over that proof and then see if you can apply that same approach to doing this corollary. Also, similar to that version where that corollary used the limit, it's worth investigating on your own, and feel free to contact me, or if this is being used in a different class, your instructor. But it's worth thinking about. Here we have something about what happens if it equals 1. Here we do not. And the question is why, right? Why are we allowed to say something when it's 1 here, but not about 1 here, okay? All right, so that being said, let's get to the proof. This has a sort of refreshingly nice proof, relatively brief. So I'm going to do the proof for A. So again, in fact, I'm going to do this before I write proof of A, because I'm going to use it for both. Because again, we know how to tackle this if it weren't the case, so I'm just going to say without loss of generality, suppose an is greater than or equal to 0 for all n. So I will also sort of point out that I didn't put bounds on these because the eventually bit makes that notationally annoying to deal with that versus this. But again, we don't care because the idea is this is going to infinity, and where it starts doesn't change the converge or diverge, right? If it starts at 7 billion, it's still going to diverge if it diverged. It's still going to converge if it converges. It'll converge to something different, but where you start shouldn't affect that. All right, so I'm just going to basically, without loss of generality, assume it's just always positive or always non-negative, so I can just deal with these directly. All right, so A. So suppose, in particular, right, so suppose nth root of an is less than or equal to alpha, which is less than 1. Then an is going to be less than or equal to alpha to the n, where alpha, again, is a positive number less than 1, right? So an's are all non-negative, so alpha is certainly not a negative number, right? Okay. Notice series, and going from wherever we started from, I'm going to go ahead and even start from 0 because I can with what I'm about to write. So this thing, n. So this, not only does it converge, I know what it converges to, right? Because this is a geometric series. So it's the first term, which is alpha to the 0, so that's 1 over 1 minus alpha. This is because it is a geometric series. Thus, by the comparison test, right, I have a non-negative, right, because I'm assuming that's true right at the beginning, sequence bounded by another sequence who I know converge as a series, so that tells me that an, wherever it starts. So just for the sake of clarity, I'm going to say it starts at 1. Again, wherever it started doesn't matter. So this thing converges. Right, and that's that, right? I have my series converges. B. Suppose now that I have nth root of a to the n is greater than or equal to 1. Again, for all n. Then, taking an nth power on both sides, I have that an is greater than or equal to 1 for all n. And, in particular, the limit as n approaches infinity of an, right? This isn't Sn, I'm not doing the series, I'm doing the term, is not 0. So the series of an diverges by the test for divergence. And that's part B. So, commentary aside on the interesting bits of the corollary, it's a very nice, sweet, short proof. In fact, it's worth, if you want, trying to take the root test and see if you can use that to prove the ratio test, which is a much more common way of going about this process. So typically the root test is shown first because it's pretty straightforward to show after the geometric test has been established. And you can, in fact, prove the ratio test independent of the root test, but you can also prove it with the root test. So that is that.